Solutions, molarity, and normality. So a solution is a homogeneous mixture of one or more solutes and the solvent. Homogeneous can be broken down into homo and geneous. So homo means the same, geneous is talking about multiple things coming together. So homogeneous or homogeneous means that everything is consistently the same throughout the solution. So if I were to take a sample from the top of the container and a sample from the bottom of the container, it would have the same chemical composition regardless of where it is in the solution. The solute is the substance being dissolved. The solvent is the dissolving agent, and it's usually the most abundant substance in the mixture. So sweet tea is prepared by dissolving an instant tea packet in water. Which substance is the solvent? So the answer here is the water. A solution consists of 25 ml of water and 75 ml of methyl alcohol. Which substance is the solute? The answer here is still the water. So in the first one, when we dissolve an instant tea packet into the water, we're assuming the water is more abundant so that the tea can diffuse into the water. So the more abundant substance is going to be the solvent. Second problem, when we look at the 25 ml of water versus 75 ml of methyl alcohol, the methyl alcohol is more abundant in volume, so that would be the solvent, while the water is the solute. Molarity is defined as the number of moles of solute per liter of solution. So we learned about moles, and we learned about molecular mass and atomic mass, and learned how to gather all that information from the periodic table. So now we can actually put it together when talking about solutions. And solutions are practically what you're going to encounter more in a laboratory setting. So note that molarity is moles of solute per liter of solution, not per liter of solvent. To make a solution of a specified molarity, you usually put the solute into a flask and then add water to the desired volume of the solution. So in order to prepare a 1 molar sodium chloride solution, you would weigh out 1 mole of sodium chloride, which when you do the math from the periodic table, 58.44 grams is in 1 mole. Then you would add water until it fills to the 1 liter mark. And that would be 1 liter or 1 molar of sodium chloride solution. Calculate the molarity of a solution prepared by dissolving 2.22 moles of hydrochloric acid in enough water to make a 0.3 liter solution. So our equation is M for molarity equals moles over liters. So they want to know the molarity. So we're going to put M equals, they're giving you 2.22 moles. And they're saying it's a 0.3 liter solution. So when we do the math here, we have 2.22 divided by 0.03, or sorry, 0.3, and we get 7.4 as our molarity. The unit for molarity is just a capital M. Okay, so now we're going to go through this problem. Calculate the molarity of a solution prepared by dissolving 9.35 moles of HBr in enough water to make a 250 ml solution. So we're going to start with our equation again. We go M equals moles over liters. So they gave us moles, 9.35. But they did not give us liters, they gave us milliliters. So we actually have to do another step here. This first step would be to convert that to liters. So we're going to do 250 mils. and this is where our unit conversions are coming into play. Since mils is on the top, mils is going to go on the bottom, and you're converting to liters. 1 liter is 1,000 mils from our conversion chart, and that's going to equal 0.250 liters. So we have 0.250 liters. So now we can actually do the division. 9.35 divided by 0.250 gives us 37.4. So our molarity equals 37.4 molar. Calculate the molarity of a solution prepared by dissolving 1.02 grams of KCl in enough water to make 755 liter solution. So we are going to start with our equation again. Molarity equals moles over liters. So they're giving us a mass here, but we know that we can convert between grams and moles based on calculating the molar mass from the periodic table. And then they give us liters over here. So we're going to put the liters where the liters go. We just have to do this extra step up front to convert the grams to moles. So when we do this conversion, 1.02 grams KCl grams of KCl is on the top, so we're going to put grams of KCl on the bottom. And we're going to do moles of KCl. Now 1 mole of anything from the periodic table, we can figure out the mass for by calculating the mass from the periodic table. So the mass of KCl, if we look at the periodic table, K, there's one of them, and the mass of K is 39.098. Cl, there's one of them, and we have 35.453. We're going to add those up. 39.098 plus 35.453 equals 74.551. And that's grams per 1 mole. So now we can put this number in here, 74.551. That's how many grams in 1 mole. So when we do the math here, we're going to multiply across the top and divide away the bottom. And we get 0.01. Like these units will do this, should say mole. Grams is going to cross off. We're ending with moles of KCl. So when we put this over here, our moles is going to be 0.013, and we'll round it to 7, divided by 755 liters. Equals 0.0000181 molar, or if we want to write this in scientific notation, we'd go 1, 2, 3, 4, 5, 1.81 times 10 to the negative 5 molar. So this one kind of put a lot together. So we got some unit conversions happening in the last problem. We've got the molar mass involving the moles and mass calculations, and now we've got scientific notation coming back. So This problem, just to walk through one more time, in order to put anything into the equation, the molarity equation has to have something in moles and something in liters. So they gave us something in liters over here, but they gave us mass. But because we know the substance, we know what molecule they're talking about, we can actually calculate the mass from the periodic table, the grams per mole from the molar mass from the periodic table. So that's what we did down here. There's 1 K in KCl. There was 1 Cl in KCl. When we got the masses from the periodic table, we just added those up and used that as our conversion factor. That's how many grams are in 1 mole of that substance. So putting them back into this equation, we had to convert 1.02 grams to moles using the molar mass conversion. And when we did that, we ended up getting 0.0137 moles. Now we took this and divided away the 755 liters, and that's how we got the molarity. So I would like you to pause the video and work through this problem. Now this problem, you have to do 2 conversions because they're giving you the moles as a mass, and they're giving you the liters as milliliters. So you'll have to do those 2 conversions as you put in the information into the problem. All right, so let's get started. So we have molarity, M equals moles over liters. So we're going to start by converting this one to moles. So we have 73.2 grams of HCl. Grams of HCl, moles, HCl. 1 mole is equal to the calculated mass from the periodic table. So what is that mass? Well, we have in HCl, we have 1 H, and that's 1.008. And we have 1 Cl, 35.453. So when we add these up, 1.008 plus 35.453, we end up with 36.461. And that's grams in 1 mole. So 1 mole is equal to 36.461 grams. So now we're going to multiply across, divide away the bottom. So 73.2 divided by 36.461 gives us 2.007. So we'll round this to 2.01. And that's for our moles because these mass units are going to cross off and we're going to end with moles. So now we have the big M equals 2.01 moles, and we're going to divide away the liters. So now we have to convert this one to liters because it's currently in milliliters. 2,902 mils. Mils goes on the bottom, and liters goes on the top. So 1 liter is 1,000 mils. We're going to multiply across the top, divide away the bottom, and we end up with 2.902 liters. So we're going to put that over here. And when we do the math, 2.01 divided by 2.902, we get 0.693 rounded. So our molarity is 0.693 molar. So now we have something a little different. What is the total volume of an 8.2 molar solution that contains 21 grams of sodium chloride? So now we're going to calculate for volume. Now, some teachers like to do the algebra up front where they move around the variables. I don't. I don't prefer that. I like to just plug it into the equation we have. Once I see numbers, then I move around the numbers. So we're just going to start by plugging in the information that we can into this equation. So our equation equals molarity equals moles over liters. So here we have 8.2 mole, or molar solution. And we don't have moles or liters. We have grams. But we can convert this into moles. So 21 grams can be converted to moles by 1 mole is equal to the calculated mass from the periodic table. So if we have Na and Cl, there's 1 Na. Na is 22.990. And then we have 1 Cl, 35.453. And we're just going to add those up. We get 58.443. Okay, and that is moles, or grams, sorry, grams in 1 mole. So we're going to put this up here in our equation, 58.443. So now we're going to multiply across the top, divide away the bottom, and we get 0.359 moles. So where we have the moles, we're going to put in 0.359. And we're going to put that over liters. So now we want to solve for how many liters. So to bring liters to the top, we're just going to multiply both sides by liters. So that becomes 8.2 liters is equal to 0.359. And then we're going to divide away the liters, or sorry, the 8.2 to isolate the liters. So that will cross off that. Divided by 8.2. So 0.359 divided by 8.2 gives us 0.0438 liters. How many moles of solute are in a 3.7 molar solution of NaCl that is 270 mils? Go ahead and pause the video and try to solve this, knowing that you do have to convert those mils to liters before putting it into the equation. All right, here we go. So how many moles of solute? So we're looking for question mark moles. Are in a 3.7 molar solution so we have 3.7 is equal to, we'll just put X because that's, we don't know how many moles, and then over liters. So we got to get this guy to liters, 270 mils. Convert this to liters. We put mils on the bottom, liters on the top so that our units can cross off. 1 liter is equal to 1,000 mils. And when we do the division here, we have 0.27. In order to isolate the X, we have to multiply both sides by 0.27. So that crosses off the 0.27 on that side, 0.27 over here. So now we get 0.27 times 3.7, and we're at 3.97 moles as our final answer. So explain how to make 3.2 liters of a 4.2 molar solution of NaCl. So we're going to use the same equation, M equals moles over liters. Molarity 4.2 is equal to X over 3.2. So in order to isolate the X, we're going to multiply both sides by 3.2. And that crosses that off over here. So 3.2 times 4.2 is equal to 13.44 moles. So, in order to make this solution, we would dump 13.44 moles of sodium chloride into a flask and then fill it up to 3.2 liters. And this would have to be a pretty big flask because 3 liters is pretty large. Now, what does 13.44 moles look like? How do we measure moles? So because moles is different depending on what substance we're talking about, some substances are more or less dense and have more molecules per cubic area, we have to consider that this isn't practical. Like we can't just dump 13.44 moles into something. So if we want to actually explain how to make this solution, we would have to convert the moles to grams, because grams is something that we can weigh out using a balance or a scale in our laboratories. So practically, if we really wanted to make this solution, we have to convert this to grams, because sodium chloride is salt, and we can weigh out so many grams of salt and then dump that into the flask to make this solution. So we're not quite done here. We do have to convert this to grams of sodium chloride. So we're going to put moles of sodium chloride on the bottom. We're going to convert to grams of sodium chloride. 1 mole is equal to the calculated mass from the periodic table. Well, we don't need to go through the math again. We calculated it previously, so we'll just use the number we had from the previous slide, 58.443 grams. So 1 mole is equal to the calculated mass from the periodic table. Now we just multiply across the top, divide away the bottom. And we get 785 grams. So we would add 785 grams to a flask and fill it to 3.2 liters. That's how we would practically make this solution. In the laboratory, you will be making solutions. You'll also be performing dilutions, which we'll talk about in the next section. But when you make those solutions, you need to know practically how much mass of the solute to put in and to what volume you would fill the solvent to in order to make that solution. All right, so pause the video and try to work through this problem on your own. All right, so we have our same equation. Now we have 1.5 molar solution. And we're going to convert this to liters. So we get 0.25 mils. Now, obviously, after you work with these numbers for a while, you can start to just know that you're going to move the decimal, or you can start to anticipate the answer when you're doing these conversions. I still write it out every single time that I perform a problem. Because when you are performing calculations in a clinical setting, you're now messing with patient results. And if you make a solution improperly, you could destroy the analyzer, screw up the calibration process, screw up the QC. There's a lot of downstream effects that can happen. So it's better to take the extra step up front and calculate it correctly up front than to go forward and accidentally make a mistake and have to go through all that headache and recall results and do corrected reports and all this kind of stuff. So I'm saying show your work. I show my work every single time. You should be thinking through any time that you have to do math on your own. So we have equals moles. We don't know how many moles over 0.25 liters. Sorry, that should be a unit of liters. 0.25 liters. So now we're going to try to isolate the x. So we're going to multiply both sides by 0.25. We're going to cross out this, and we're going to do 0.25 times 1.5 to get our moles, and that's 0.375 moles. Now, as I mentioned previously, we don't have a method of weighing out moles. So we're going to convert this to mass, because mass we can weigh out on a scale or balance in our lab. So moles down here. We're going to convert to grams. Now 1 mole is equal to the calculated mass from the periodic table. We did calculate this previously, so we're just going to go ahead and use this number, 36.461. So we're going to multiply across the top, divide away the bottom. And we get 13.67 grams. So I'm going to weigh out approximately 13.67 grams of HCl, and I'm going to put it in a flask, and then I'm going to fill it to 250 mils or 0.25 liters. And that's how I would make this solution. Okay, one more problem. Go ahead and pause the video and work through this one. Okay, so our equation that we've been working with, so we have 2 molar solution is equal to x over, we have 375 mils, we're going to convert that to liters. And we're going to divide that and get 0.375 liters. So now we're going to do 0.375 liters. So in order to isolate the x, we have to multiply both sides. That's going to cross that out, times 0.375. So 0.375 times 2, 0.75 moles. So we're going to go ahead and convert that to grams. So we're going to have moles on the bottom. I'm not sure if we did KCl yet. Oh, we did. So we have 74.551 grams in 1 mole. So we're going to multiply across the top and divide away the bottom. .9 grams. So what we would do is we would put 55.9 grams of KCl in a flask, and then we would pour in solvent until we got to 375 mils. All right, the last concept for this video is normality. Normality is a unit of concentration used in chemistry, especially for acid-base and redox reactions. It tells you how many equivalents of reactive species, like hydrogen or hydroxide ions or electrons, are in 1 liter of solution. So normality is equal to molarity times equivalents per mole. So an equivalent is the amount of a substance that will donate or accept 1 mole of hydrogen ions, donate or accept 1 mole of electrons in a redox reaction, or react with 1 mole of ions in a precipitation reaction. So in hydrochloric acid, there's 1 hydrogen ion per molecule. So 1 molar of hydrochloric acid is 1 normality, or 1 normal, because there's no like subscript here. There's 1 hydrogen that we can see. So 1 molar of this substance produces 1 normality worth of hydrogen ions, or 1 mole of hydrogen ions. Here we have 2 hydrogens, so that's going to produce 2 hydrogen ions per molecule. So 1 molar of H2 is 2N, because 1 mole gives off 2 moles of hydrogen. When we look at this one, our hydroxide, there's 2 of them. So there's 2 hydroxide molecules, or 2 hydroxide ions that can be given off per molecule. So if we do a half molar of the OH, it's 1N. Because if we had 1 molar of CaOH2, it would have been 2. But since they're asking about a half molar, then that would be half of 2. So that would only give us 1 normality. So what is the molarity of the following solutions? And here's our equation down at the bottom. Normality equals molarity times equivalents per molecule. So this one is 2NHCl. We're talking about 2 molar HCl, because molarity and normality are the same when these are not. There's only 1 mole per molecule. So now we have 25N of H2. So what would be the molarity of that? Well, let's go ahead and calculate this one out. So normality equals molarity times equivalence. So it's given 25 normality is equal to our molarity, which we don't know, times, there's actually 2 equivalents in here in this substance. So we're going to go like that. And then in order to isolate our variable, we're just going to divide away by 2, divided by 2. 25 divided by 2 gives us 12.5. So now we have 3N, and they want to know M. So we're going to put it into this equation over here. N equals M times EQ. So our normality was given as 3 equals M, we don't know, that's what we're trying to calculate, times there's 2 equivalents of the hydroxide ions. So in these problems, you're always looking for how many hydrogens or how many hydroxide groups. This is a hydroxide group, this is a hydrogen. So there's 2 of those. In order to isolate the variable here, we're going to divide it by 2, divided by 2. 3 divided by 2 is 1.5 molar. So what is the normality of the following solutions? Well, if we have 2 molar and there's only 1 hydrogen, it would be 2 normality. If we have 1 molar and there's 3 hydrogens, it would be 3 normality. If we now have 0.5 molar and there's 2 hydrogens, we can go ahead and put this one into the equation. So normality equals the molarity times equivalence. So we were given 0.5 for the molarity, and there's 2 equivalents. So 0.5 times 2 gives us 1. Then we have this over here. There's only 1 equivalent, so we can just use the 2. Since there's 1 equivalent, 2 molar is 2 normal. Now, molarity and normality are pretty rarely encountered in a clinical setting. However, if you do get something, and if it comes up on the qualifying exam, you should have some familiarity with this topic. So let me know if you have any questions.